Hi guys, this will be the last thing we do together this year. We're going to take all of the trig with the right triangles that you did a couple weeks ago, and we're going to combine it with all of the angles in standard position and reference angles that we did this past week. And I'm going to try to keep it as simple as possible. You're going to need to be a little bit more fluent next year when you actually take pre-calculus or trigonometry as far as radian measures go. But here, let's have a quick review that'll set us up for this lesson. So let me just remind you, a couple weeks ago, we talked about special right triangles. And all I need you to remember is that when we have a right triangle with two 45-degree angles, if one of the acute angles is 45, the other one has to be 45 because they add up to 180. So a right triangle with a 45-degree angle is one of our special right triangles. And the ratio between the hypotenuse and the two sides is always going to have this square root of 2 factor. If I know my side, or one of the legs, I can multiply by square root of 2, but usually we're going to know the hypotenuse and need to divide by the square root of 2 to get to the value of the legs. If it's a 30, 60, 90 triangle, then we have some other special ratios and factors. So if I know the hypotenuse, that short leg that is always opposite the 30-degree angle is going to be exactly half of the hypotenuse, right? That's the factor of 2. We can go multiply this leg by 2 to get to the hypotenuse, but usually we're going to know the hypotenuse and need to go backwards, so we're going to divide by 2. And then as long as I know this short leg's value, then I can always just multiply by square root of 3 to get the long leg's value. And the long leg is always opposite the 60-degree angle. So we're going to need this when we talk about our special angles in our unit circle. And so that's from last week. This was one of the pages I just had you print. These are called special angles because all of the angles are either 45 degrees, which from the x-axis, right? That's all of these that are smack dab in the middle of the quadrants. Notice they all in radian measure have a denominator of 4. Those are all what we call our 45-degree reference angles. And those will relate back to this 45, 45, 90 triangle. And then the others are either 30 degrees or 60 degrees from the x-axis. Notice all the 30-degree reference angles, the ones closest to the x-axis, notice that they all have a denominator in radian form of 6. And then the 60-degree angles, the ones that are 60 degrees from the x-axis, they are all in radian measure have denominators of 3. The special angles that are furthest from my x-axis, which is 60 degrees from my x-axis, they all have denominators of 3. So we'll relate back to this as well and how it relates back to this special right triangle. So I'm going to put these two aside and start with our fresh angles today. So let's talk about how we could use our reference angles to find the sine and the cosine of an angle that is 45 degrees in standard position. So I want you to think about a rotation of 45 degrees. So we're always going to start on the positive x-axis as 0 degrees, and we're going to rotate up 45 degrees. So that angle is going to be smack dab between 0 degrees and this right angle of 90 degrees. So this is an angle in standard position of 45 degrees. Now we also talked about, let's zoom in there a little bit, here we go. We also talked about the unit circle having a radius of 1. So if I were to draw a circle around my origin with a radius of 1, then that is this distance right here is 1. And then I'm going to drop a vertical line to my x-axis. Notice that the blue vertical line is opposite my angle in standard position. So this is the angle that is opposite. And then the side of this right triangle here in green, this would be the angle, the side that's adjacent to my acute angle of 45 degrees. And then 1 is opposite the right angle, so it is the hypotenuse. So I'm going to write hypotenuse here, right? So my hypotenuse has a length of 1. And now this is what we call one of our special right triangles. It's a 45, 45, 90 triangle. And so what I know about the ratio between the hypotenuse and the sides is that they have a factor of square root of 2. If I go from the larger hypotenuse to the legs, I have to divide by the square root of 2. So I'm going to do that. So this opposite length here is 1 divided by the square root of 2. And then hopefully we remember how to rationalize our denominators. So I'm going to multiply by square root of 2 over square root of 2. And so my opposite length is 1 times square root of 2 is square root of 2. And then square root of 2 times square root of 2 is square root of 4. Square root of 4 is a whole 2. And so this is my opposite side right there. Now purposely, because my radius was 1, my hypotenuse is 1. So when you go back to your definition of sine, so let's go back to the definition of sine from a couple of weeks ago. The sine of an angle is going to be the opposite side's length divided by the hypotenuse's length. And then on purpose, we made the hypotenuse 1. That's what a unit circle does, is purposely make the hypotenuse 1. So our sine in a unit circle, let's see, a unit circle has a radius of 1. So the sine is always going to be the opposite length. And so let's write that. So in a unit circle, if the radius is 1, then my sine is simply going to be the opposite length. Notice that this opposite length, if I'm thinking of this as the origin, is also the y-coordinate of that point right there. It's the y-coordinate. So what we found here was that the sine of my 45-degree angle was the square root of 2 over 2. And that's always true, always, 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 always. The sine of a 45-degree angle is always going to be the square root of 2 over 2. Now, the cosine of an angle is going to be the cosine of my angle, which is 45 degrees in this case, right? It's going to be the adjacent length over the hypotenuse. But here's the good news. Because this is a special right triangle, and I know the two legs have the same length, and the opposite and the adjacent are exactly the same length, so the ratio to the hypotenuse is exactly the same. So for all 45-degree reference angles, the sine and the cosine will look like square root of 2 over 2. Let's see. Okay, so of course it can't always be that simple, right? So I'm going to move this up a little bit, and we're going to talk about a couple of other things. So notice in the second example that they give me my angle in radian mode. And again, when you get to trig or pre-calculus, you're going to want to be fluent in this radiant mode. But right now, let's just go ahead and change this to degrees so that we can just look at it as far as our special right triangles in degrees. So remember that pi is 180 divided by 3. So 180 divided by 3 is 60 times 2. This angle we did last week, we can change it into a 120-degree angle. And so if you revert back to your circle here, you can see that 2 pi over 3 is indeed 120 degrees. And so it's going to be somewhere up here. And that is this is quadrant 1, this is quadrant 2, right? It's important that we know that in quadrant 2, my opposite side, so we're going to draw our unit circle here again, around. This is the angle that is theta. Let's talk real quick about the reference angle. The reference angle is the angle that goes to the x-axis. So we're going to say that because this is 120 and this is 180, this angle between them is 60 degrees. So it's a 60-degree reference angle, we say. And then we're going to drop this perpendicular line to the x-axis. That's a vertical line. So because on purpose we make our radius 1, that means our hypotenuse of this right triangle, the one that's opposite the right angle, is going to have a value of 1. So my hypotenuse is 1. And then the vertical side that I just dropped, right, that's opposite my reference angle. Okay, so that's going to be my opposite. And then the horizontal side of my right triangle is going to be the side adjacent to the 60 degree that's not the hypotenuse. So, and then up here we talked about the fact that when the radius is 1, my sine is simply the opposite side's length. So let's talk about what that would be. So because my this triangle that we created is a special right triangle, it's got a 90-degree angle, it's got a 60-degree angle, that forces this angle to be 30 degrees, and that makes my adjacent the short leg, and it makes my opposite side the long leg, you can see, of a special 30, 60, 90 triangle. So again, I know the hypotenuse is 1, and I know the short leg is exactly half of the hypotenuse. So my short leg, which is the adjacent, which we've now said is going to be the cosine, is the same as the adjacent over the hypotenuse. On purpose, we made the hypotenuse 1, right, because it's a unit circle. So the cosine is going to be this adjacent length, and it's going to be half of the hypotenuse, so 1 over 2. And then the sine is going to be the opposite length. And so we would always just take our short leg and multiply it by the square root of 3 to get the long leg. So this 1/2 times the square root of 3, right, would just end up looking like the square root of 3 over 2. Okay, now that's all well and good, okay, but notice that this angle is different than the angle that would have been up in the first quadrant. And so we need to talk about whether or not my sines and cosines are positive or negative. So that's what we're going to look at here. Now, this is in quadrant 2. Notice that my y-coordinates, my vertical distances, are in the positive direction. So this sine is going to be positive because it's in quadrant 2, it's in the top half of my graph where all of my y-coordinates or vertical coordinates are going to be positive. But my adjacent goes from the origin, it's heading in the negative direction. We're going to say that the cosine for anything that's over here in the negative x direction, they are going to be negative. Only because we're in quadrant 2 will I get positive sines, the y's are in the top half, but negative cosines because I'm on the left side. So this is going to be a negative 1/2.